Stanford University.
So let's talk about supersymmetry. Supersymmetry has to do with fermions and bosons. Now, and the relationship between them, symmetries between them. So actually, before we talk about supersymmetry, we should talk again about fermions and bosons. And I want to tell you some odd and peculiar facts about fermions first. No, before we even talk about fermions, let's talk about rotations in space. Now, we always say that a rotation by 2 pi is equivalent to no rotation at all, but it's not true. It's not true. Let me assure you that if I take my hand like this and I rotate my wrist by 2 pi, it is not like doing nothing. But then I tell you if I rotate it by 4 pi, which I will do for you in a minute, all right? If I rotate it by 4 pi, it's equivalent to doing nothing. So you want to see me rotate by 4 pi, don't you? You don't think I can't do it. Oh, yes, I can. Right? Okay, we started this way. Palm up. Rotate by 2 pi, it starts to hurt. Palm up, and I come back to nothing. All right? This is a topological theorem about rotations in space. It's a topological theorem, and let me explain the topological theorem to you. I've proved it. All right? I proved it. I don't need to prove it mathematically. I proved it by hand waving. Right? Right. I proved it by hand waving. Exactly right. But let me tell you what the theorem actually says. Here's the theorem. Take a box. The box has walls. In that box, put a basketball or some sort of object and connect that basketball to the walls by strings, any number of strings. It doesn't matter. Just connect them by strings. It's connected to the front wall, back wall. Now, I tell you, and I think you'll believe me, that if I take this ball and rotate it by 2 pi, I'm going to get a hell of a tangle. The strings are going to get all tangled up. And the question is, can I untangle them by looping them over the ball, without rotating the ball further? Rotate it around by 2 pi. Can I get rid of the tangle and bring it back to this configuration? Anybody know the answer? Rotate it by 2 pi. No, you're not allowed to rotate the box. The box is fixed. So this is a theorem about rotations of the ball keeping spatial infinity. The box really represents spatial infinity, keeping the spatial infinity fixed. You're not allowed to rotate the box. So question, can I or can I not undo that rotation? Not yet. Suppose we do not. We simply rotate by 2 pi, and we ask, can we undo it by moving around the strings, taking them over the ball, doing whatever we have to do. The strings are flexible. They're even stretchable, but they're unbreakable. And they're connected both to the ball and the boundary. All right. Mathematically, it's the same operation as trying to undo this. The theorem is that a rotation by 4 pi, that you can undo it. So the answer is for any rotation by an even number of 2 pi's, you can undo it by moving the strings around and taking them over the ball and so forth. And it's a topological theorem about the equivalence between a rotation by 2 pi and no rotation at all. They're not equivalent, really. A rotation by 2 pi is not equivalent topologically to no rotation, but a rotation by 4 pi is. This is kind of unintuitive, but it's true. Okay. Let's now come to the properties of wave functions of particles, and now I'm thinking simply about their spin. Imagine nailing down the position of the particle, and the only thing that's important now is the spin of the particle. And the spin of a particle is described by a quantum state. Let's call it S for spin. I'm either thinking about fermions or bosons, In the case of fermions, the spin is half integer. In the case of bosons, it's integer. Now the question is, what happens to the state of a particle if you rotate the particle by 2 pi? Now you can imagine for an electron actually doing this in the laboratory, how would you actually rotate the spin of an electron by 2 pi? Anybody know a good way to rotate the... You can grab it with your hand and rotate it, but that doesn't work so well. Magnetic field. You put it in a strong... Two ways you could do it. You can put it into a strong magnetic field and then rotate the magnetic field around until it comes back. Okay? You can actually do something else. If the spin happens to lie in the vertical direction, you can put a magnetic field in and just have it precess by itself around there. You don't have to rotate the magnetic field. Either way will do. You can rotate the spin of a charged particle simply by grabbing it with a magnetic field and rotating it. What happens to the state of a spin particle when you do rotate it by 2 pi? Well, usually we say it has to come back to itself. After all, rotation by 2 pi is nothing at all. But we found out that rotation by 2 pi can do something. So we might suspect then that if we rotate the spin of a particle by 2 pi, it gets, something happens to it. The simplest thing that could happen to it is it could just get multiplied by a number. Why multiplied by a number instead of some other more complicated operator? Well, that's a little complicated. Why? Because we secretly believe that no experiment will detect the rotation by 2 pi. And if we multiply the wave function of a particle, for example, by a phase or by a -1, that won't change any physics. We really secretly believe nothing experimental will be detected by rotating by 2 pi. One possibility is it gets multiplied by 1. Another possibility is it gets multiplied by a phase. But here's what we do know. If we rotate by 4 pi, all right, if we rotate by 2 pi, and that gives us some sort of phase, at e to the I theta, then rotating again by 2 pi, we'll just square this. And now we know that rotating by 4 pi is equivalent to doing nothing at all. Okay, that's the topological theorem. Doing nothing at all had better just give us back the same state. So the mathematical argument says that psi squared must equal 1. And there's only 2 possibilities. Psi is equal to +1 or -1. So we could have either possibility. When you rotate a particle by 2 pi, just its spin, you either multiply it by +1 or you multiply it by -1. An interesting question is, can you ever imagine, just as a side issue, is there ever any experimental observable consequence of the fact, the potential fact, that the wave function of a particle might change sign when you rotate the particle? And it was generally considered to be a totally unphysical operation. You could never detect it. In other words, here would be the experiment. You take a whole family of electrons all prepared identically. You take half of them and you stick them into a magnetic field and you rotate the magnetic field by 2 pi. You take the other half and you do nothing with them. At the end of the day, is there any experimental difference between them? And the answer is, for that experiment, the answer is no. No, you cannot tell the difference which ones got rotated. But you can do something else, and I'll tell you what it is. You can do a 2-slit experiment. Just to tell you the meaning of this odd mathematical fact, you can do a 2-slit experiment in which you take electrons. Let's start with a single electron, not multiple electrons, or one by one. We take electrons one by one, and we send them through. The electron either goes through the upper slit or the lower slit. We don't know which. And we're not allowed to look, because if we look, we will destroy the interference pattern over here. Okay? There's some interference pattern over here. But now what we're going to do, without looking at whether the electron is here or here, we're going to place a magnetic field over here, a B field over here, we'll also do the same thing over here. And we'll imagine that the electron gets temporarily trapped in this region by whatever. All right, temporarily trapped and then re-emitted. If we do absolutely nothing to these B fields, we'll still get some interference pattern here. Either the electron goes up through here and gets stuck in the B field and then gets re-emitted. The B field is not very interesting, or same thing over here. But now we do the following. We do the two-slit experiment, and while the electron is trapped in one of these two, we rotate one of them and not the other. We rotate one of them and not the other. Then the wave function here may or may not get multiplied by a minus sign, but let's suppose it does. The wave function in here does not get multiplied by a minus sign. It either gets multiplied by a minus sign or a plus sign. If it gets multiplied by a plus sign, nothing, no detection. But if it gets multiplied by a minus sign, and this one, the wave function coming out of here does not get, what does that do to the interference pattern? It shifts it. It shifts it up half a wavelength. It shifts maxima to minima. Okay? So yes, you can detect this odd sign change, but only by splitting a beam of electrons and then rotating half the beam and not the other half beam. So it is an experimental, it's a real phenomenon. But if you were to take the whole experiment and rotate all of it, both magnetic fields simultaneously, then you detect nothing. Okay? All right. It's very similar in mathematical structure to the story that if you rotate the ball without rotating the box, you can detect the fact that you've rotated it by 2 pi. If you're allowed to rotate the whole thing, ball and box, of course you can't. So it's a similar kind of thing. Yeah, if you rotate, exactly. If you rotate the magnetic field by 4 pi, the effect goes away. Right. And this incidentally has been done in the laboratory. It was an experiment that was suggested by Aharonov and myself in 1967, and it was actually done. Yeah, okay, so now you could do experiments with electrons, you could do experiments with charged ions of various kinds, and you could see which ones fall into the category of getting a -1 and which ones don't. The ones that don't have a -1 are the ones where the interference pattern does not shift. The ones that do get a minus sign are the ones where the interference pattern does shift. Right? The answer is all fermions get the minus sign, all bosons do not get the minus sign. That's first of all, it would be an experimental fact if you really did the experiment. It's also deeply embedded in the structure of the mathematics of quantum field theory and quantum mechanics. All right, so that's an interesting distinction between fermions and bosons. Yeah?
How does the analogy with the strings work?
The analogy with the strings. Well, roughly speaking, bosons behave as if they weren't connected to the, by strings to the wall. Fermions have some memory of having been rotated by 2 pi, so they have a sort of connection to things which remembers whether they rotated by 2 pi. This is just a mathematical way to see the topology, the topological fact that rotation by 2 pi is not so innocent, whereas rotation by 4 pi is. But once you know that, I think we forget about this.
Are they in the same quantum state?
Which?
One's that rotated 2 pi and one that isn't rotated?
Yeah, well, no, in this experiment, yeah, the quantum state of this one is localized over here, the quantum state of this one is localized here. All right, so what's the idea? The idea is you create one way or another a superposition of states in which the electron is here or it's here. Not 2 electrons, an electron which is either over here, so a wave function which consists of 2 bulges, probability a half for the electron to be over here, probability for a half for the electron to be over here. Now, both of these electrons now, after you've, not both of the electrons, one electron, but if the electron is here, we're actually putting it inside a box, put it inside a box. So we create an electron over here. We split the beam, which means we create a superposition of states where it might be here or it might be here with probability a half. And then we rotate this box, put a magnetic field in it. We rotate it. We don't ask whether there's an electron in it or not. Whether or not there is an electron in it, we rotate the box. Now, to start with, the wave function was a sum of two terms. Psi1, which is the wave function in here, and psi2, which is the wave function here. Psi1 plus psi2 was the full wave function. Right? Now we rotate the right-hand box without, if we rotate both boxes for the electron being a fermion, then the whole wave function changes sign. If the whole wave function changes sign, remember all physical quantities are proportional to the wave function times its own complex conjugate, and the minus sign will cancel out. But now supposing we rotate one box relative to the other. Then what happens is after the rotation, this wave function has changed sign, this one has not. Let me give you a consequence of that. If these two wave functions were identical about reflection about the center here, that would say that after the rotation, the wave function must vanish at the center here. If psi1 and psi2 have exactly the same shape, and let's even suppose, yeah, all right, after we bring them back together again, by symmetry, the wave function will vanish at the center here if the wave function is odd. If the wave function is even, then after we bring them back together again, it doesn't have to vanish at the center. So an interesting consequence of this is if this one is a fermion and we rotate by 2 pi and then bring the wave functions back together again, we will never find the electron at the center. That's an example of an interference phenomena. But the point is that there is a difference between psi1 minus psi2 and psi1 plus psi2. And that difference can be experimentally detected.
Is it the case that if you don't do a full rotation, that basically the amount of rotation is half as much for a boson or twice as much or something like that?
Well, there is something like that, but it's not, yeah, there is. If you look for the electron in such a way that you can tell afterwards which one it was in, then the interference pattern is destroyed. You do not want to do that. You want to.
What happens if, instead of a screen, you test? Say you put it all right, all the spins are all in one direction, and then at the screen you test the resulting spin. Will that destroy the interference pattern?
All the spins are in one direction. Okay, they're all in the same direction.
Oh, I see. They still stay in the same direction, just get a minus sign. Okay.
Well, after the rotation, yeah, that's right.
Okay.
That's correct.
Okay.
That's correct. Yeah.
Is it true that if you didn't turn it 2 pi to turn it just pi?
Oh, then it's certainly detectable.
Then it would
change the
destroy
direction of the spin.
Then the interference pattern would be destroyed.
Right. The interference pattern would be completely destroyed.
Basically, as you tune it, you can tune it till you get an interference pattern.
Yeah. That's right. If you rotate that spin, you tend to rotate the spin by anything except either 2 pi or 4 pi, you'll lose some of the interference pattern. If you actually rotate it by 180 degrees, you completely destroy the interference pattern. Right. That's correct. You can't interfere an upspin with a downspin. You can only interfere things which are otherwise the same. Yeah. Good. All right. Good. So we now have some bits of information about fermions. They change sign on the rotation. Bosons don't. Now, let's come to yet another question. Let's come to a question about Feynman diagrams. The kind of Feynman diagrams I have in mind now are very, very simple. They have no external lines at all. They're just Feynman diagrams in the vacuum, empty space, and they consist of nothing more complicated than a single closed loop. A single closed loop, it could be an electron, or it could be a photon, for example. It could be a fermion, or it could be a boson. And this Feynman diagram, among other things, controls, it's first of all, among other things, the amplitude that you start with nothing and you get nothing. So it's part of the vacuum structure. The diagram has a value. That value is a contribution to the vacuum energy. Let's not try to understand precisely why that's so, but just like the diagram which is attached to the particle here shifts the energy of the particle, a diagram like this in free-floating space would shift the energy of a vacuum. The question is, does it shift it up or down? And we're going to find out that the answer is different for bosons and fermions. So let's think about the sign, just the sign of a diagram which looks like this for fermions or bosons. Now, amazingly, without doing any work at all, we can prove the desired result, which I will show you now.
No work at all. No work at all.
Very little. Very little. Here's the way we do it. Let's start with the boson case. Well, let's start, no, we can take both cases simultaneously. And let's begin with two loops. In other words, what is a loop? A loop is the production of a pair of particles and the subsequent annihilation of it. Or you can just think of it as a particle going around in a closed loop in space-time. You can either think of it, particle goes around in a closed loop in space-time, or more physically, less colorfully, it's a production of a pair of particles, particle-antiparticle pair, and then the annihilation. Okay, here there are two loops, and let's ask about the sign of the diagram associated with just one loop. It can either be positive or negative. All right. What about two separate loops like this? The Feynman diagram consisting of two separate loops is just the product of the Feynman diagrams for each loop separately. If there's a plus sign for one loop, then there will be a plus sign for two loops. What about if there's a minus sign for one loop? There'll still be a plus sign for two loops. So the answer for two loops like this, disconnected loops like this, is always positive, whether or not the sign for one loop is negative. Now let's do the following. Let's assume that our particles are fermions. Let's break this over here and look at it right in the middle at t equals 0, while these two things are here. Let's put them close enough together that they almost overlap. What happens to the amplitude for a system if you interchange two bosons? If you take the two bosons and exchange them? Plus sign. The wave function for bosons is always symmetric, which means if you interchange them, plus sign. What happens if you take two fermions and interchange them? Minus sign. Right? That's the property of fermions and bosons. For fermions, the wave functions are antisymmetric, and so if you interchange the two fermions, you get a minus sign. For bosons, it's a plus sign. So we can compare two things. And the first thing, we take these and we don't interchange them. That's just two loops. And the second thing, before closing it up, we interchange them. We just interchange which one is which. What happens if they're fermions? If they're fermions, we get a minus sign. If they're bosons, we get a plus sign from here. We've managed to go from 2 loops to 1 loop. This is 1 loop now. This is just 1 loop. It's 1 loop. We went from 2 loops to 1 loop just by interchanging 2 particles. 2 loops necessarily has a plus sign. If the loops involve fermions, then there's a sign change when we interchange the 2 particles. So a single loop like this for fermions necessarily has a minus sign associated with it. A single loop for bosons has a plus sign in the amplitude. The consequences of this are profound. What it says is that the contribution to the vacuum energy of a loop of fermions is negative. The contribution of a loop of bosons is positive. Okay? That's very interesting. We have this very strange puzzle about the vacuum energy that we talked about last time. The vacuum energy, whatever it is in nature, is very, very small. We call it dark energy. It's extremely small. The amount of it in this room is extremely negligible. And the naive calculation in quantum field theory would give an answer 123 orders of magnitude larger. It is at least at minimum interesting that the quantum field theory answer can either be positive or negative, and that it's negative for fermions and positive for bosons. The answer depends on all kinds of details about the particle. It depends on the mass of the particle and other things, depends on its charge, depends on all sorts of things, but at least we've encountered a way to be able to get both plus signs and minus signs. The fact that they cancel out to 123 orders of decimal places is bizarre, but at least we have the possibility of canceling contributions. Right? Bosons, all things being equal, will give, equal means the same mass, the same charge. All things being equal, a boson and a fermion will give the same contribution to the vacuum energy, except one with a plus sign and one with a minus sign. Now, that does not explain why the vacuum energy is 0, but it does perhaps create a thought in your head. Perhaps there is a lot of cancellation between fermions and bosons. What it would take to have an exact cancellation would be, we're going to discuss this, you would necessarily have to have for every boson a fermion with exactly the same mass. These diagrams do depend on the mass of the particle, and we don't have to know the details of how they depend on the mass of the particle, but if for every boson we had a fermion with exactly the same mass and the same properties in every other respect, then we could imagine, or we could conceive, that the theory might exactly cancel out the vacuum energy. That's one of the things that supersymmetric theories can do. I will tell you later what a supersymmetric theory is. I haven't told you yet, but that's one of the things that supersymmetric theories can do. They can cancel out precisely the contribution to the vacuum energy. Now, we know in nature, we know with absolute certainty that there is not, for every particle, a image or reflection particle. For every boson, there is not a fermion with the same mass, and for every, and vice versa. We know that. An example would be the electron. Is there a particle in nature with the same electric charge as the electron, but which has the opposite, which is a boson instead of a fermion? We would know if there were. We would know with certainty. And the way we would know is because in collisions, for example, electron positrons come in. Here's an electron, here's a positron. What happens to an electron at E minus E plus? What do they make when they collide? A virtual photon. Now, if there was a partner, let's call it a partner, to the electron, which was a boson with exactly the same charge, then it could be produced, let's draw this a dotted line, then it could be produced from the virtual photon with exactly the same probability as the electron, if it had exactly the same mass. And we know this doesn't happen. Just go in a laboratory, scatter an electron and a positron, and what comes out is an electron and a positron, not a boson with the same mass and charge. So we know that, in fact, in nature, there is not this symmetry or this reflection symmetry. It's not a reflection in space, but reflection of boson into fermion. We know that that's not true, but still it's interesting to contemplate the fact that if we had a theory which was sufficiently symmetric, we'll discuss what we mean by sufficiently symmetric soon, but if it was sufficiently symmetric between bosons and fermions, we would at least have a chance of canceling out all this vacuum energy. We would at least have a chance. So it's a thought to keep in mind. Another thought to keep in mind, can it help us at all with the self-energy of bosons? Here we have, where is it? Here we have these Feynman diagrams which give rise to quadratic divergences in the mass of a boson. Even if the mass of the boson, even if the bare mass of the boson was initially 0, in other words, the bare mass, these diagrams would create huge masses for the bosons. Okay? That's a problem. That's a problem for all the reasons I said. We'd like to get rid of that problem. We would like to create a theory in which bosons don't get this huge amount of mass from renormalization or from whatever we want to call it. We already have a theory in which fermions don't get these huge amounts of masses. Remember, we discussed a few minutes ago that for fermions, because of this left-right switch, fermions, in many situations, the self-energy of a fermion will not be infinite. For example, if you start with a fermion with no mass at all, it will not get this big mass. Now, supposing for some reason your theory was concocted in such a way that even after all this renormalization takes place, even after all the worst-looking Feynman diagrams you can imagine, there was enough symmetry, enough structure in the theory that made certain that the fermions and the bosons traveled in pairs and always had exactly the same mass, the partners. Then, because the fermions don't get any mass, if they didn't start with any, it must also be true of the bosons. Why? Well, I'm not saying that we can make such a theory. In the face of it, it seems like we can't make such a theory because obviously the bosons do get big masses from self-interaction and the fermions don't. But here's what you can imagine. As an example, take the various Feynman diagrams which contribute to the self-energy of the boson. You might have a Feynman diagram as an illustration, just as an illustration, which looks like this. But you might have another Feynman diagram, these are all bosons, but you might have another Feynman diagram where what runs around in the center here is a fermion. Boson going around the loop, fermion going around the loop. Fermions and bosons always have opposite signs for these loops. So one can think then, one can imagine that if there was enough symmetry and if every stage that symmetry was correctly preserved in detail, the cancellation of the self-energies of the bosons might also be exact. This cancellation of the self-energy for the fermions, that's exact. If it starts 0, it ends 0. If there was such a symmetry between fermions and bosons, which was rigidly enforced by the mathematics of the theory somehow, then we might imagine that there are theories where the bosons do not get these huge self-energies. That in itself is not good enough. We know that there is not an exact mass equivalence between fermions and bosons. But it's a start. Let's take a little break. Let's take a break for a few minutes and then come back to this. So to zeroth order, the hypothesis is not that there is, when I say to zeroth order, I don't mean in any mathematical sense. I mean in some rough approximation to what the story is, that for every particle in nature, there is a partner of the opposite, somethingness, the opposite Fermi-bosonous, the bosonosity. I don't know what the right word is. You know what I mean. For every fermion in nature, like the electron, there is another particle which is a boson with integer spin, with the same charge. Yes, with the same charge, same electric charge, and so forth. Now, I would say with the same mass, but we know that's not true. Okay? So not with the same mass. And for every boson, there's a fermion. For every fermion, there's a boson. This would entail basically doubling the spectrum of all of the elementary particles. How about the fact that they don't have exactly the same mass? In fact, their masses are going to be quite different. Well, if the masses were equal, we would discover that all of this bad junk cancels out exactly. Supposing the masses are almost but not quite equal, we still might have a lot of cancellation. Perhaps not a complete cancellation, but an approximate cancellation, if the masses were not exactly equal. We don't care, for example, that there might be some self-energy for these bosons. We just don't want it to be huge. Right? So a diagram like this and a diagram like that will not exactly cancel unless the masses running around in the loop here are exactly the same. But if they're not exactly the same, but close, we might expect a good deal of cancellation, approximate cancellation, enough cancellation to keep from getting this explosively large answer. And in fact, we will talk about supersymmetry. Supersymmetry is nothing but, well, it is in fact much more. But among other things, it is this idea that every particle has a partner of the opposite statistics is the right word. Statistics means Fermionness or bosonness. That's what supersymmetry is. It's a symmetry which relates fermions to bosons in such a way that every boson has its fermionic partner, its fermionic superpartner. They come in superpartner pairs, and with precise mass equivalence of the particles' partners, we would have precise cancellation of this kind of thing, of the vacuum energy and so forth, with almost degeneracy. Degeneracy means equality of masses. We can have approximate cancellation. That's the working hypothesis, that the things which control and keep these phenomena from running away and being enormously large is cancellation between fermions and bosons. Now, we're not, we are going to say more about it and perhaps even do a little bit of the mathematics of it. It's extremely abstract, as I said. That doesn't mean difficult. It just means abstract. But that's the zeroth order idea. Every particle comes equipped with a superpartner. Those superpartners have never been discovered in the laboratory. Not one of them, not a single one of them has ever been discovered in the laboratory. The implication is they must be a good deal heavier. I showed you how you might detect the superpartner of the electron. You collide a pair of electrons, you create a virtual photon, and then you create the charged particles which are the partners of the electrons. The fact that they have never been discovered means that no experiment has ever had enough energy to create these particles. These particles must be quite massive. How massive? Basically at the edge of detectability. Beyond the edge of detectability, that means hundreds of GeV, hundreds of times the mass of the proton. Now, is this really as far-fetched? That sounds very far-fetched, that we just, by accident, all the particles, all the partners happen to be too heavy to be seen, and that really sounds like really, it's not good practice. Well, it's not really that bad, because when you look at these supersymmetric theories, what you discover is that some of the particles have the natural natural tendency, the natural property that the only way that they can get mass is from the Higgs phenomenon. Others can have mass without the Higgs phenomenon. It turns out in these theories, just mathematically, that exactly half the particles, some of them fermions, some of them bosons, necessarily owe their mass to the Higgs phenomena, which is another way of saying they must be massless until there's spontaneous symmetry breaking of the electroweak of the Higgs boson phenomena. And the other half are allowed to have mass without that. So it's almost natural to say that half the particles might be a good deal more massive than the other half. It is, for most of us, it's a little bit of a stretch, the supersymmetry idea. It's just a little bit too lucky that we just haven't seen any of it yet. On the other hand, there is some rationale for why the particles that we've seen happen to be the ones which have low enough mass to be seen, and why the ones we haven't seen could conceivably have higher mass. So we have to wait and find out. But that's kind of what LHC was designed to find out. Originally, it was designed to detect the Higgs boson. But by now, I think it's generally conceded that, well, the Higgs boson is going to be there, generally conceded. And it turns out to be the hardest thing to discover in the list of things that you might want to discover. The much easier thing, and in a sense more profound and much more interesting in the point, from the point of view that we don't know if it's there or not, is the supersymmetry. So what's going to be studied is collisions at high enough energy to produce these superpartners if the superpartners are low enough mass to be detected. Now, first question, how do we know that they're not way off at enormous mass? What would happen through this cancellation if half of the particles were at enormously large mass? How massive? I don't know, the Planck mass or something. Then the cancellation would be extremely bad, and it would be just as bad as not having these heavy particles at all, or practically as bad. And instead of having infinite self-energies, you would have self-energies which were as big as the Planck mass. So if you want this supersymmetry to play the role of somehow protecting you against enormously large self-energy corrections, the mass difference between the bosons and the fermions cannot be too big. In fact, a couple of hundred GeV, beyond that, the cancellation would be too poor to have a decent explanation of why the self-energy of the Higgs boson was not too big for experimental reasons. So if the role of supersymmetry is to keep the Higgs boson from getting much too much mass, then the difference between the masses of the particles and their superpartners cannot be all that big. It has to be, roughly speaking, within the experimental range of the LHC. That's the logic. That's the logic of what's going on. Superpartners and the symmetry to protect against having the Higgs boson dragged up to enormously high energy and everything else with it. That's the role of the superpartners. The masses of the particles in the superpartners are known not to be equal, but how different can they be and still do the job that they were intended to do? And the answer is not too far from experimental detectability. Yeah, question. I saw some. All right, let's start over here.
Yeah, if I understand what you're saying is that in the aggregate, hope the terminology is correct, the statistics of the fermions and the bosons in a universal scale must roughly even out, or there would be different measures of vacuum energy. Is that
Yeah.
correct? That is different than saying...
Well, vacuum energy is not really our problem. I just illustrated vacuum energy as one thing that supersymmetry can do. We're really more interested in the self-energy of the bosons, of the Higgs bosons. What does it mean in the aggregate?
A whole bunch of...
Yeah, they all have to be close to the, you know, they all, the mass splittings between the particles and the superpartners cannot be too big.
Yeah, but that's different than saying every fermion and boson need to have some relationship. In other words...
No, okay, wait, yeah. No, I know what you're asking. I know what you're asking. Right. One possibility is that in aggregate they cancel. That would not require an exact matching between fermions and bosons. It would just require the sum of all fermions to approximately cancel against the sum of all bosons. Right. That's deemed to be an accidental cancellation. As uncomfortable and as surprising and fine-tuned as the original problem was. You can say, well, at least the fermions give you the opportunity to have some negative signs, and that's true. They at least give you the opportunity, but if it was just a question of in aggregate cancellation, then you would say, well, this was an extraordinary, exceptionally lucky accident. But if you can build theories, where this cancellation is more natural, if you can build theories with a higher, at the moment, the way I've stated it, it's not very natural. So the question is there a mathematical framework that contains these kind of symmetries between fermions and bosons, which also can explain the fact that they're not exactly equal in mass in a natural way, and in which the symmetry between them, by natural, nobody knows exactly what natural means. Natural means it's sort of mathematical consequence of some reasonable postulates that these things approximately cancel each other. That would be much, much more satisfactory than just saying the whole bunch of them accidentally cancel against the whole bunch of the other ones.
But one more time, that's true if you assume reductionism. If you don't assume reductionism, it may be very natural that in aggregate they cancel out. I don't know what that really means, but it's...
I know what you mean. I think that just means we don't really understand or know what's natural and what's not natural. Yeah. No, this is true. This is true. There's no question that we're groping around for answers to these things. One hypothesis is the mathematics of supersymmetry and spontaneously broken supersymmetry. We haven't discussed that, but there's a notion of spontaneously broken supersymmetry which will create mass differences for particles. The mathematics of that conceivably could be something which would, not conceivably, I mean, we know theories where it really will do the job. The only question is it the right theory, and is it the only theory which will do that? And at the moment, yes, but that doesn't mean it will stay that way. Yeah.
I seem to recall that before the top and bottom quarks were directly detected, I think it was at SLAC, there was the measurements of the yields of different particles got accurate enough that it was likely that there were three families.
Well, it was the tau lepton that was discovered.
Yes.
Yes. That was the third of the leptons.
So what I think I recall is that the Feynman diagrams of all these different virtual particles that can be excited and annihilated, and the sum of all that gives a measure of what I'm going to call the yield. Is the accuracy of the particle physics now getting to the point where you can see anything?
Okay, that's a good question. All right, here, let me phrase the question a little bit differently. good. That is a very, very good question. Let's come back to this electron-positron story and the superpartners as an illustration. I said there wasn't enough energy, or at least it had better be that the superpartners are heavy enough that current experiments have not had enough energy to create them. But you might ask, are there some possibly indirect evidences? The kind of indirect evidence might be something like this. Here's a Feynman diagram with here's electron, positron collide, create, I don't know how to draw the superpartners. Let's just draw the superpartners with dotted lines. But there really isn't enough energy to create the superpartners, so they have to annihilate again. And that means we just think of this as a virtual process which violates energy conservation a little bit for a short time. Now you might ask, well, doesn't this diagram modify slightly what the electron-positron process is like? And can't you detect that difference? So it becomes a question of high precision, what's called high precision electroweak or high precision phenomenology of the particle physics, where you don't actually look for the particles, but you look in very high precision experiments that are already done. You look for evidence of this kind of thing. Well, what I can tell you is, to some extent, the answer is that these high precision experiments do constrain things, and they really are pushing you to the edge of the parameter space. In other words, it's getting a little dicey as to whether you can really fit supersymmetric particles into the theory. It's still by no means ruled out by these high precision electroweak experiments, but it's a very good question. I think the answer is, if we would have an electron-positron collider with at energy of maybe, I'm not sure about my numbers here, but a few times larger than SLAC, we might be able to do very high precision experiments and rule out supersymmetry on the basis of high precision experiments. We don't have, why an electron-positron collider, incidentally? Why is that better for high precision? And the answer is electrons and positrons. What do you collide at the Large Hadron Collider? Hadrons. Protons, basically. Protons are a mess. They consist of several quarks, and what you're really trying to do is collide quarks together, and it's a mess. All right? It's a mess. It's a much more messy thing than two elementary particles colliding together like an electron and positron. So an electron-positron collider is a much better machine for high precision. If we had such a machine now at, I don't know, 1 GeV or something like that, we could probably do business with the high precision end of it. But we don't. What we have, like Donald Rumsfeld said, we go with the machine that we have. And
We don't know, we don't know.
right, the known knowns and the unknown knowns.
If the probability of the process, electron-positron annihilating and then creating two superparticles is a little bit different from the other way, wouldn't it make sense?
The other way being what?
Two superparticles colliding and creating
Well, we have to get the superparticles before we can do the experiment.
That's what I'm getting to. If there was a universe where you had a lot of superparticles, they would go down, wouldn't they?
Yeah.
Because it wants to be in a lower energy state.
Yeah. These superparticles are not expected to be stable. They're expected to be rather unstable. They will decay to known things fairly quickly. So the likelihood that there's remnant superpartners of the electron floating around in space, not likely. They will have decayed long ago. So I think the answer is that there's good reason to believe that there are no freely floating around. You'd have to make them somehow. How do you make them? By having enough energy to make them to overcome their mass. All right? And that's what we're trying to do. Yeah.
I thought the superpartners were one of the candidates for the dark matter.
Oh,
So
yeah.
that seems at odds with what you just said about the
It is possible that one superpartner might be stable. The reason one, because they have to decay to something. All right? In many theories, they have to decay to something which is still a superpartner. You can't get rid of all superpartners. So yes, but those superpartners might, and very likely, would be electrically neutral. The reason is because any kind of electric charge is likely to make them even heavier. So it's quite likely that, whatever the stable superpartner is, it's called the lightest superpartner, the LSP, the lightest superpartner. The lightest superpartner very likely is electrically uncharged. That doesn't mean it's undetectable. You would detect it in the laboratory, but it wouldn't be this thing here. The lightest superpartner may well be stable. It may well be the dark energy. But most likely there would only be one of them which would be stable, so all the remnant particles in the universe that were superpartners would just decay to that one, and that one, if it were not electrically charged, would not be so easy to detect. But in principle, yes, you would detect it.
How do you know that it's not the coupling constant that's keeping you from seeing these things? Maybe they have a different coupling constant.
No. One of the things which is very, very important. Good. Okay, so that's an interesting question. Let's draw some diagrams. Let's take two Feynman diagrams. I'll do it for the vacuum energy, but we could also do it in principle for oh, no, let's do it. Yeah, let's do it for the vacuum energy. Here's two Feynman diagrams, one of them involving the electron going in a loop, and the other involving the superpartner of the electron going in the loop. They will have opposite sign, and they will cancel each other if they're well matched, okay? If they're well matched, if they're matched enough in mass. Now let's draw another Feynman diagram in which a photon goes here, and a photon goes here. Will they match, and will they cancel each other? Yes, they will still cancel each other, but only if the electric charge of the electron and the electric charge of the superpartner are equal. Otherwise, there will be a discrepancy between these two, a numerical discrepancy between them, which would lead again to a big divergent answer. So it's important in these arguments that you follow through at every level and make sure that the cancellation takes place. And that typically requires electric charge of the partners to be the same as the electric charge of the particles. So, yeah.
What does the partner of the photon look like? It's got mass?
The real partner of the photon has mass. Now, how? Well, this is what I'm telling you. We do not have a collection of particles which have the same mass as the known particles. We don't. So supersymmetry is not a precise thing. At best, it's an approximation. It's an approximation in which, in the exact supersymmetric theory, if it existed, the superpartner of the photon would be massless. It's not. These particles have names, incidentally. Typically, if the ordinary particle is a boson, then the superpartner is an ino. For example, the photon partner would be a photino. The W boson, its partner would be a wino or a wino. The Z particle, it would be a xeno, I suppose. And there's not such a neat name for the superpartners of the bosons. They're typically scalar particles, and so you put an S in front of their name. So that leads to disgusting names like the selectron, which is, not nice. The superpartners have peculiar names. The gravitino would be a fermionic version of the graviton. What are the names? What are the peculiar names are there? There's a hexeno, which would be a fermionic version of the Higgs particle. Inos are always fermions. Except when they're ordinary fermions, then they're not inos, they're just electrons, quarks. What would you expect the bosonic partner of a boson to be? A squark. A squark. A squark, right? Yeah. So there are squarks and enos of all kinds, and none have ever been detected yet. Okay. I think they're going to be detected. My guess is that this is going to work, but I don't know. We'll find out. I'm just guessing. Let's talk about one last thing before we go home.
How is the spin of the ordinary particle related to the superparticle spin?
Okay, the superparticles, if the ordinary particles are bosons, then the superparticles are always fermions. So if the ordinary particle is a boson, then typically the superpartner is a half spin. And that's true whether it be whether the original particle is a scalar or a gauge boson. The partner is a half spin particle. If the ordinary particle is a half spin particle, then typically the partner of it is a scalar particle, which means no spin. But it's always this interplay. They always differ by half a unit of spin. So if the ordinary particle is half spin, the superpartner would be spin 0. If the ordinary particle is spin 0, like the Higgs boson, then the corresponding fermion would be a half spin. So they always differ by a half unit. Yeah.
Would these new scalar particles be subject to,
Which what?
the new scalar superpartners, would they be subject to spontaneous symmetry breaking?
In principle, the answer could be yes. In fact, that would be a very bad idea. Yeah. So that must not happen. Right. So let me repeat the question. The question is, if there are all these additional scalar particles around, that means scalar fields. And scalar fields are things which we've seen can have the spontaneous symmetry breaking phenomena. Could we tolerate having an additional, some other spontaneous symmetry breakdown? No, we couldn't. That would be a bad thing to happen. So that would not be good. Yeah.
So the fermion then would be the superpartner of the Higgs.
The Higgsino.
Yeah, would that have any special properties?
Well, I suppose it has all kinds of special properties, but nothing, I mean, to an experimental particle physicist, I'm sure we could conjure up all sorts of special properties, but nothing. Well, remember, the fourth power is simply another way of talking about a Feynman diagram where two particles come in and two particles go out. So there will be matching interactions. One of the things that has to match are the interactions of the particles, which we haven't talked about at all yet. So there will be matching phenomena to take the place of the 5/4 terms, yeah. But it won't be exactly what you think, but related. Yeah.
The theorem about the rotations, does it hold in higher or lower dimensional spaces?
Wait, say it again?
The theorem that says that the rotation in 2π rotation doesn't bring you back to the same state.
You're asking whether there are higher and lower dimensional versions of it? Yeah, there are. The answer is yes. There are. It's an odd, even dimension business, a peculiar the discrepancy between odd and even dimensions, whether there is or is not an analog to that. There can be analogs to it. Yeah.
Because it seems easily in 2 dimensions it wouldn't happen, right? In 2 dimensions.
In 2 dimensions, it doesn't happen. Right. In 2 dimensions, there are things which are in between fermions and bosons. They're called anyons, any meaning any value of the spin. So in 2 dimensions, 2 spatial dimensions, there's a generalization to any spin called anyons. And they happen in condensed matter physics. Excitations in certain condensed matter systems have basically arbitrary spin. But this is not for us to discuss now. Okay, I was going to talk about one more thing, just about what would the world be like if it were exactly supersymmetric? Interesting question. Supposing it was exactly supersymmetric, how different would the world be? How different would we be? How different would biology be? How different would chemistry be? And the answer is very different. So let me just show you why it is not possible. Certainly we don't live in a supersymmetric world. Supersymmetric meaning exact degeneracy, exact equivalence between the masses of the particles and the superpartners. We do not live in such a world. Could we live in such a world? Would such a world be one in which ordinary chemistry would exist, for example, biology, anything else that we are familiar with? I think not. And let me show you what would happen to chemistry. Among other things, atoms, of course, have electrons. If there was a superpartner to the electron, it would be a boson, right? It would be a boson. It would have exactly the same mass and charge of the electron if we lived in such a supersymmetric world. There would also be a partner to the photon. We would call it the photino. And because the photon is massless, the photino would also have to be exactly massless. So let me show you what would happen to an atom. Not a hydrogen or a helium atom, but let's start with some atom with 3 electrons or 4 electrons or 5 electrons. In a hydrogen atom, of course, the single electron moving in it moves in the lowest orbit, in the lowest Bohr orbit. In helium, we have 2 electrons also both moving in the lowest Bohr orbit. So both hydrogen and helium, the electrons all move in the lowest orbit, in the stable form of these elements. Let's go next to lithium. Lithium has an extra electron, and the extra electron is in the next orbit out because of the, what's the principle which says that the lithium atom can't have 3 electrons in the same orbit? Pauli exclusion principle. Pauli exclusion principle is most definitely associated with the fact that the electrons are fermions. Now, what would happen to this outer electron? Remember, the outer electron has more energy than the inner electrons. It wants to go down to the lowest level, but it can't get in there because it's being blocked by the other ones, and it just doesn't want to allow another electron in there by the Pauli exclusion principle. How would it get down to the lowest level? It would get down to the lowest level by emitting a photon, which would carry off some energy, and the electron drop down to the lower level. But it's blocked. It can't happen. Now, imagine there was also a photino, which was also massless. What could happen to this electron, and not what would happen, well, not could happen, but would happen, is the electron moving around would emit a photino, not a photon, a massless photino of exactly the same properties or similar properties to a photon, and then what would it become? This electron. It has to change. This is a fermion. Here's a fermion, and a fermion gets projected out. What has to be left over? A boson. Right. If a fermion comes in and emits a fermion, it has to become a boson, but what would that boson be? It would be the superpartner of the electron, which is called the selectron. Now, the selectron is a boson. It has no trouble getting into the lowest orbit. So it drops down to the lowest orbit, and you would not have a lithium atom. You would have a slithium atom or something, but the main thing is that the electron would be replaced by something that drops down to the lowest Bohr orbit. Now think about a big atom. Chemistry, what does chemistry do to? Chemistry is due to the physics of the valence electrons. Valence electrons, what would happen to the valence electrons in a big atom? They would all just drop down by the same mechanism. They would all drop down to the lowest energy orbit and all crowd in on the lowest energy orbit to the extent that they can get in there. They would not be blocked by Fermi statistics, and so they would all sit in the lowest energy they could get into. What kind of thing would you have at the center here? At the center you would have a Bose condensation of selectrons. Rather than an atom with valence electrons, you would have an entirely different thing. Now, I don't know what the world would be like. I just know whatever it would be like, it would not have conventional chemistry. It would have nothing like conventional chemistry. Whether you can use such atoms as tinker toys to create molecules and so forth, I rather doubt. They're all going to be crowded in at small distances near the nucleus. I rather doubt that there's anything resembling ordinary chemistry of molecules and so forth, but I don't think anybody's ever worked this out, incidentally, what the world would be like in such a supersymmetry. But it would not resemble our world, that I can be sure of.
So the selectron would emit a photino?
The electron would emit, if there was an electron there. If there was. In other words, if we started with something that looked awfully much like a lithium atom, it would very quickly become a silithium atom with a photino traveling out.
Wouldn't there be a coupling constant associated with that?
Yeah, but yes.
So it could be hard to do.
It could be what? Yeah, but we know what that coupling constant is. It's the electric charge. So we know it's not hard to compute what would be the lifetime of a lithium atom if the electron could drop down. It would be short. It would be just a microsecond or something. So one can calculate, and these would not be terribly small numbers. They would not be so no, you're not going to get away from it that way. So it's an interesting fact that why isn't the world supersymmetric? I don't know, but I know that at least I couldn't be here if it were. So it's an amusing fact.
So let's assume that if there are supersymmetric particles and the symmetry is reasonably badly broken, and so we have a big mass separation.
Well, okay, now the question is what's big and what's small? What are we comparing with? Now, if we compare with the mass of the proton, it's big. If we compare with the unification scale or the Planck scale, it's terribly tiny. So, right, but keep going now.
So the question is, what do we think the reason for this broken symmetry is? In other words, how come we're here?
Well, one possible answer is if the symmetry weren't broken, we wouldn't be here to ask it. Right. Right. I think that's the best answer we have. They could, right. On the other hand, it's not very hard to break these symmetries. It's not very mathematically terribly hard to break them. It's rather generic. But not that generic. I mean, there certainly are completely supersymmetric theories. They're the ones we understand best, incidentally. The mathematical theories, not because of these weak interaction issues, just as a mathematical fact. The quantum field theories that are best understood are the supersymmetric ones. They have so much special structure to them that they often can be almost exactly solved. Much more is known about them than the others. They have all sorts of fabulous special structure to them. Okay, next week, more on supersymmetry. We'll have supersymmetry until you're sick of it.
For more, please visit us at stanford.edu.